Okay, going to take a look at Momentum Worksheet 2, Problem 7. This is the one with the collision between the car and the truck. So it says, at the intersection of Ogden Avenue and Eola Road, a small car of mass 900 kilograms traveling east on Ogden collides with a pickup truck of mass 1,500 kilograms traveling north on Eola. Let's do that sketch. So you're going to say, here we go. Okay, so say we have our intersection here. Right? Okay, so here's Ogden and Eola, right? And so we have a car, just this little car that is headed east here, okay, on Ogden, okay? And they tell us that the car has a mass of 900 kilograms, okay? And you say, hey, that is going to collide with a pickup truck of mass 1,500 kilograms heading north. Pickup truck, big truck, okay, headed north. This is 1,500 kilograms, okay? That's the truck, that's the car, okay, called C and T. Okay, good enough, all right? And it says the two vehicles, they're going to hit and crumple and stick together, and they're going to slide off 16 meters, immediately after the collision. They're moving at 16 meters per second, 24 degrees east of north. Okay, so you're going to say, okay, 24 degrees east of north. You say that means north is this way, 24 degrees east. They're going to be sliding like that. Okay, at 16 meters per second, and then 24 degrees to the east of north. Okay, that's what it looks like afterwards. So we got our before and our after here. Okay. All right. So here we go. So what they'd like to know is they'd like to know the speed of each vehicle just before they hit. Okay, and this is something that we can figure out with momentum. Okay. The first thing you notice about this is this looks different than the problems we've done previously, because these things are moving in two-dimensional space now, instead of just moving along a line and bouncing into each other, yeah? So it's a 2D problem. It turns out that when I look at momentum, momentum's a vector, it's an arrow, and so we can look at momentum in different directions, right? And we can add vectors and subtract vectors, and we can break them into components, which is what we're gonna do. So the idea is, if I consider the car and the truck as my system, okay, then you're like, what outside forces might be acting on them to cause impulses? And you're like, okay, well, gravitational force goes down into the page in our top-down view here. Is that going to be affecting our motion in this direction? Like, no, it's in this way. Normal force from the street? No, that's not going to matter. Any other outside forces? And you're like, well, maybe some kind of friction from the street. Well, we're going to look at it immediately before they collide and immediately after they collide. That friction force isn't going to have enough time to change anything. Well, be a very big force from the collision of these things shoving on each other, car and truck. That friction force is negligible in comparison. That's the logic. So I don't need to worry about friction forces. We're just looking at it immediately before, immediately after. That friction isn't going to have enough time to have a big impulse on our system. So what I'm going to say is, that outside impulse is going to be zero if I treat the car and truck as one system. Okay, and so, hey, that friction is negligible compared to the forces the car and the truck shove on each other. It's going to have such a small effect. Now, over time, as they skid, slide, that's going to, impulse of friction is going to slow it down to a stop. Yeah, sure. But just immediately, during the collision, just before, just after, so that the friction doesn't have enough time to really cause a significant impulse. So here's the deal. How am I going to set this up to find those initial velocities? I'm trying to find the velocity of the car at the start, and I'm trying to find the velocity of the truck at the start, right? You know what I mean? So when I do this, it's a two-dimensional thing. I can go ahead and break it down and look at each coordinate axis independently, like we did with projectile motion. We looked at the horizontal motion and we looked and did a calculation for it, and we looked at the vertical motion and did a calculation for it. We're going to do the same sort of thing here with our east-west motion and our north-south motion, doing separate calculations for each. So what I'm going to do is I'm going to do conservation momentum twice, once for the east-west, once for the north-south. That's going to look like this. East-west, I'm going to say F delta T is delta P, and I'm going to do for the north-south, F delta T is delta P, okay? In both cases, we're saying that if my system is the car and the truck together, that impulse is negligible, outside impulse from friction, you don't have to worry about it. So I'm just going to have car and truck, change the momentum of the car and change the momentum of the truck, but I'm just looking at the east-west. Is it okay with you if I do coordinate axes like this and call this x and y instead of east, west, north, south? It's a little quicker to say just x and y, all right? We're going to call that way positive. So this is just going to be basically just looking at the x components, okay? And this one will be looking at just the y components. Delta P for the car and delta P for the truck, but just the vertical, the y, the north-south components, okay? All right, if I do that, what does this look like? Delta is final minus initial. This is going to be P of the car at the end, just the x component, plus minus P of the car at the start, just the x component, plus momentum of the truck at the end, just the x component, minus momentum of the truck at the end, just the x component. All right, now when I do that, are any of these terms going to be 0? And you say, yeah, look at the car, or sorry, the truck. Did the truck have a horizontal momentum at the start? And you would say no. So this term, the horizontal momentum of the truck at the start, with final minus initial, that should be initial. This term, that initial momentum of the truck at the start, that's going to drop right out for us because the velocity of the truck in the x-axis was 0. Okay. All right. Let's go to this equation now, if you don't mind. I'll set this up, and then we won't worry about the specifics. No, we'll finish this one first. Okay. Now, what about at the end here? The way I'm going to do this is going to be, I'm going to plug in mv for momentum, mass of the car, velocity of the car at the end in the x direction, minus mass of the car, velocity of the car at the start in the x direction. Okay, plus momentum, mass of the truck, velocity of the truck at the end in the x direction. There we go. All right, looking at this equation, do I know the mass of the car? Yes, I do. I know the mass of the truck, yes. Do I know the velocity of the car in the x direction at the start? This is what I'm trying to find. That's this horizontal velocity, right, at the start. That's what I'm trying to find. Do I know the final velocities now? Hey, the car and the truck at the end, they're moving together, aren't they? They'll have the same final velocity, and their x components will be the same. I'm going to take this velocity, this 16 meters per second at the end, and I'm going to need to split it into components, okay? I'm going to choose to divvy it up like this. I'm going to make my angle to the x-axis. That's what I learned from math class. I'm used to doing to the x-axis. If this is 24 degrees, this is going to be 66 degrees, yes? So this would be the hypotenuse times the cosine of 66. That'll be 16 cosine 66. This is hypotenuse times the sine of 66, right? That's that. So I know the values for the horizontal and vertical velocities at the end. So I do know these v's. I know everything in this line except v of the car at the start in the x. I can solve for that now. Okay? All right? What would that look like? If I just plug the values in, I would have the mass of the car, 900. Gosh, I had intended to do color coding for this problem, but I botched it. Velocity of the car at the end in the x-axis, that's the 16 cosine 66. Okay? Minus mass of the car, 900, times velocity of the car at the start in the x. This is what I'm trying to find. Plus the mass of the truck, 1,500, times the velocity of the truck in the x, same as the velocity of the car in the x, 16 cosine 66. So I can solve that equation for the velocity of the car on the x-axis, right? If I do that, I'm just going to go ahead, I'm going to do that in my calculator here off to the side. Here we go. Okay, right. So 900 times 16 cosine 66. I'm not sure if I did that right. Yes, I did. Very good. Okay. Okay, I got a value of about, rounds off to 17.35 meters per second. Okay. I'm going to do a very, very similar thing for the vertical axis now, right? Splitting this up. I meant to color code for the two vehicles. I ended up color coding for the two directions. All right. Anyway, hey, change momentum for the car. That's going to be momentum of the car at the end, just doing the y components, minus momentum of the car at the start, doing just the y component, plus change momentum for the truck in the y. That'll be momentum for the truck at the end, the y component, minus momentum of the truck at the start, just the y component. Okay. Are any of these terms zero? And you say, yeah, right? You say, look at the truck. At the the car. At the start, did the car have a vertical momentum? No, it didn't. The vertical momentum of the car at the start is zero, so that term drops out. Okay. Just like the truck didn't have a horizontal momentum at the start, the car doesn't have a vertical momentum at the start. It's heading straight east. So at this point, I can put in, let's go ahead and put it in here. This is going to be mass of the car times velocity of the car at the end in the y. This term dropped, plus mass of the truck, velocity of the truck at the end in the y, minus mass of the truck, velocity of the truck at the end, at the start, final minus initial, at the start in the y. All right. I know all of these values except for y. Well, I don't know this initial velocity of the truck in the y. This is what I'm trying to find. But I do know all the rest of this. We can plug in our values and solve. Okay. So if I do that, mass of the car, velocity of the car at the end in the y, that's just that vertical component, that's 16 sine 66. Okay, plus the mass of the truck, 1500, velocity of the truck at the end in the y. Again, 16 sine 66, they're moving together at the end. Okay, minus mass of the truck times the velocity of the truck at the start in the y, that's the thing I'm trying to find. Velocity of the truck at the start in the y. That's what I'm trying to find. I can punch in my calculator and solve that. If I do that, what am I going to get? Okay, and I got 23.39 rounds to 23.39 for that velocity of the truck and the y at the start. What did I just say? 23.39. Ta-da! Okay, and that's that problem solved. So, hey, what's the takeaway? The takeaway is I can calculate conservation of momentum separately for the x-axis and for the y-axis. I can treat them separately. And I can do my equation. And when I do that, I'll just put in the components in the x direction for all my velocities and the components in the y direction for all my velocities when I do those values for the two axes. And that's it. That's how you handle a 2D collision. You really just do the same calculation you would normally. You just do it twice, right? Once for the x-axis velocities and once with the y-axis velocities and momentum. And that's it. That's it. So yeah, that's problem 7. That's problem 7.